Assalamualaikum and hi everyone. So today we are going to continue to our second subtopic in chapter 2, which is DeMorgan Theorem. So DeMorgan Theorems are actually two sets of rules or laws. Okay, this is the first DeMorgan Theorem and this is the second DeMorgan Theorem. Okay, there are two set of laws that is developed from Boolean expressions for and or and not using two input variables a and b. For example, the two rules of theorems allow the input variables to be negated and converted from one form of a Boolean function into an opposite form. Okay, so we will look into these two theorems in detail. Okay. This is the first DeMorgan theorem. In this DeMorgan theorem, it says that when two or more input variables are n and negated, when two or more input are n, okay, and then negated or complement here is equivalent to the O of the complements of the individual variables. It means that this circuit, okay, this combinatorial logic is equivalent when these two variables is complemented, okay, and then OR together. Okay, so this is actually will give you the same output. We can prove this equivalent by using this truth table. Okay, you can see here we have two input A and B. Okay, this is the NAND gate and this is the individual complement OR gate by using the DeMorgan theorem. Okay, if let's say both values are 0, okay, and then the output will become 1, okay, because A dot with B is equivalent to 0 and you negate it, it will become 1. But if we are using the DeMorgan theorem, okay, we complement each variable, which is 0 become 1, okay, and then we add this value by using OR gate and it will get the same result with the previous one, okay, and so on, and therefore it is proved that the NAND is equivalent with the first DeMorgan theorem by using the negative OR logic. Now we look into the second DeMorgan theorem. In this DeMorgan theorem, it proved that when two or more input variables are OR and negated, they are equivalent to the n of the complements of the individual variables. So you have a NOR gate here. You OR variables and then you negate it by using a NOT gate here. Okay, is actually equivalent to the second DeMorgan theorem, which you complement individual input variables and then you AND it together. This one can be proved by using this truth table. We have A and B. Okay, when A and B are both 0, so the output A plus B is 0 here and you negate it, it will become 1. But by using the DeMorgan theorem, you complement this individual input and then it will become 1 and 1 and you dot product it or AND it and the output is also 1. Okay, and then you can see for the rest of the value in this truth table. So it proves that the NOR gate is equivalent to the second theorem of the DeMorgan theorem. Okay, by using the negative AND. Negative meaning that you complement the individual input first and then you AND them, right? So what if we have more than two variables? So if we have more than two variables, for example like this one is equivalent to A, B, and C. Similar to the first DeMorgan theorem, if we have more than two variables, for example A, B, and C, this one is equivalent to A plus B plus C. Alright? Okay, so that's all for the DeMorgan theorem. Okay, this is the example of DeMorgan theorems. You have, this is the initial logic, okay, and then you get the equation by using this logic. So this one is a NAND gate, so you get BC with the negate symbol, okay, and then the result of this one you put into the NOR gate, Okay, and then this is the end result. And then actually this one, you can simplify this equation by using a DeMorgan theorem. So by using the DeMorgan theorem, okay, you will get this one A plus, okay, you will get A complement, and then you dot product with BC, and then you complement it, okay. So you will get this one. And then from here, you can have the new logic diagram, which is simpler than the original one. Okay, so this is the usage of the DeMorgan theorems in simplification of the logic diagram. Okay, so this example, we are going to do it in the class later. Okay, so I'll see you again. Okay, thank you.